Hi 253. In this video we're going to continue discussing section 9.1 where we've been working with power series and specifically approximating functions with these infinite polynomials. Before we continue, I'd like you to read an example. I'd like you to read example 1 on page 591. So do that first, pause the video, go read the example, and then come back and we'll continue. So don't watch the rest of the video until you've actually read that example. All right, so welcome back. Now that you have read example 1 on page 591, what I'd like to do is consider how we can improve these approximations that we're using with these polynomials. The problem is so far we've approximated with lines and with quadratics, but what I'd like to do is get an even better approximation by using some more terms, right? So perhaps we could just agree based on more factors here, more characteristics of our function. So how do we get these better approximations? To get a better fitting polynomial, right? So instead of fitting it with a line or with a quadratic, perhaps we should use more terms. I mean, why couldn't we fit it with a cubic or a quartic or a quintic or a sixth degree polynomial or a seventh degree polynomial? There's no reason we couldn't. We just have to figure out what the characteristics would be to get the shapes to match. Yes. So the problem, or not the problem, but the idea here is that we want to use more derivatives, right? Because the derivatives, remember, are what are allowing us to make the shapes the same, right? We got the direction to be the same using the first derivative. We got the concavity to be the same using the second derivative. We could use the third derivative to get the way that the concavity changes to match, right? We could use the fourth derivative to get the way the rate of change of the concavity changes, right? So we just need to make sure that more derivatives agree, right? As long as we have more derivatives agreeing, the shape will be better and better approximating the shape of our function. So these kinds of polynomials where we're going to use more and more derivatives to approximate our functions, these are called Taylor polynomials. Okay, so just to give you an idea of what this would look like, let's look at a figure, one of our figures from our textbook that actually moves, right? So let's uncheck that for a second. So here's the graph of sine of x, and what I'd like you to notice is that we're going to approximate the function sine at 0, because here notice a is equal to 0, so we're going to approximate sine at 0 right here. So what does the first order approximation look like, right? What p1 of x is going to be the tangent line, right? So that's the what we call first order Taylor polynomial. It's the first order approximation, right? Polynomial degree 1 that is approximating sine at 0. Yeah, it's pretty good, right? And you can see that as a changes here, as we move along, the tangent line approximates what the function is doing there, agrees in terms of value and direction, but not concavity, right? Doesn't agree in terms of concavity. Let's take away the first order and let's instead do a third order. This would be what you would get if you approximated the function using a third degree polynomial, right? A cubic, yes, okay? And approximating it at a equals 0 looks pretty good, right? And as you move the little cursor, you notice that the cubic changes shape so that it exactly mimics what the curve is doing wherever you're trying to approximate it, right? Yes? And of course, the coefficients that are producing the shape of the cubic are changing based upon the value of the function of sine, the direction, the shape, as well as the change in the shape, right? The change of the concavity would be that third derivative, right? Giving that last piece for the cubic. Okay, take that away, the fifth order. So notice we're getting even better approximation. It matches more overall even, right? Yes? Okay, better than the cubic did, see? The ends of the cubic here sort of stopped mimicking the sine function as you went out further, but the fifth order, right, here, the fifth order is mimicking it even more, right? Okay, and you can see that as you move a, it sort of models the sine function more, right, in a greater interval, right? It models it, yes? Let's take those away and look at the seventh order. Okay, now this one you might think, oh, way down there it doesn't agree at all, but look how much of it does agree, yes? Okay, and as you move a around, you can really see that at a equals 0, you're getting a pretty decent approximation of what sine is doing, even fairly far away from the center, right, from a when a is equal to 0, right? Okay, so this is what we're going to try to do with these Taylor polynomials. We just have to figure out how to do it, right? So the problem is that we need to come up with all of the coefficients for the powers of x in our polynomial, right? What do we come up with for the coefficient in front of x cubed? You know, we don't know what we're supposed to come up with. Well, we can generalize the process we used when we came up with the coefficients in front of the for the constant and in front of the x and in front of the x squared. We can generalize this and notice a pattern. So this is a definition from your book for Taylor polynomials. If we've got a function f and we have derivatives defined at a where we want to approximate our function at, we call the nth order Taylor polynomial the following. Its center is going to be at a. We denote it Pn, right? P sub n, the nth order Taylor polynomial. And it has the property that it matches f in terms of value, slope, or direction, like I said, concavity, and all derivatives up to the nth derivative at a, meaning all those features of the graph are going to match. That is, you have this statement here in terms of the derivatives all matching, value, slope, direction, concavity, all that stuff, right? Change of concavity. The nth order Taylor polynomial centered at a is the following. P sub n, there's the agrees in terms of value, agrees in terms of direction or slope, yes, agrees in terms of concavity. We've already seen that one. Well, you didn't see it as a factorial. We just had a 2 down here, but 2 factorial is just 2, isn't it? Yes? So far up to here, we've got we agree. Yes, that would be modeling it with a quadratic so far. But the idea is you can generalize this process and keep going, right? You can approximate it with an nth order polynomial, and the coefficients are found by doing this calculation right here. Yes, the coefficients in front of each of the powers of x are determined by performing this calculation here, right? So all you have to do to figure out what the coefficient needs to be in front of x to the n, right? If you want to center it at 0, for example, right? But you can center it wherever you like, meaning approximate the function wherever you like, is take the nth derivative of f, plug in a, divide by n factorial. That will be the coefficient in front of x minus a to the nth. Okay, and that'll allow you to construct the entire polynomial. So more compactly, we can write it as follows, because of course this right here is a finite sum. It only has n terms. Yes, there are only n terms, which means we can use summation notation for this, but it's not an infinite sum, right? It's not an infinite series. It's a finite sum, right? So we could go from k equals 0 to n, c sub k, that's just going to be the number living in front of all the powers of x, some power of x minus a here, and the coefficients in front of the x minus a's are going to be given by the following. Some kind of derivative of f evaluated at a over a factorial. Yes, and so here in the first one for our quadratic, we saw this was 2 factorial, right? Because that would be the power, would be the term containing the x squared. So that would be when k is 2. Yes. So that's specifically our notation here for the nth order Taylor polynomial with the coefficients given by this formula right here. Yes? So what I'd like you to do is pause the video for a moment and read through example 2 on page 593 and then example 3 on page 594. And then once you've done that, come back. Welcome back. Now that you've read example 2 and example 3 on pages 593 and 594, you have seen how we're able to approximate functions like sine and e to the x with polynomials of various orders. I think you did orders 0, 1, 2, and 3, at least in example 3 with e to the x. You also were able to see how these Taylor polynomials can allow you to get a value for e, right? When you plug in a value for e, that's easier than maybe using your calculator or something. For example, if you do e to the 0.1, that's easier, or not, that's more difficult than plugging in 0.1, excuse me, into your polynomial, right? So again, the idea here though is that we're approximating, right? We're simply approximating. So what happens then when we're approximating is that we're generating some kind of error, right? And in example 3, it actually asks you to find what's called absolute error by doing this kind of an approximation. And we're going to fine tune that idea of error in the rest of this video. So really the issue is that when we approximate a function using a Taylor polynomial, we get a little bit of an error. We're missing a little bit of the value of the function, right? We can think about this just like we were when we were working with infinite series and thinking about it in terms of a remainder, right? We used this word before to represent the leftover stuff, right? And the remainder here is just going to tell us how good our approximations are when we're using a Taylor polynomial to approximate the value of a function at a specific place, right? So let's call it something specific just like we did before, right? So let's let Pn be the Taylor polynomial of order n for f, right? It doesn't say anything about where we're going to be approximating the function at, because that'll come into play later, okay? The remainder in using Pn to approximate f at a point x is given by the following, right? It's just the difference between what? The value of the function and the approximation using the Taylor polynomial, right? Notice that this remainder depends upon x, right? It depends upon where you are choosing to plug in a value of x for, right? Let's say, for example, you are approximating your function f at a, right? Let's say a is 0, right? You're approximating your function using a polynomial at a. You're centering it at a, right? That's where you want it to give you an approximation at. You use that polynomial then to say, okay, well, what is the function at approximately 0.1? Right? And you plug in 0.1. You're not going to get the exact value of the function because you're using an approximation. You're using your polynomial to approximate the function, right? But the remainder, how much you're off by, depends upon that 0.1, right? You have to plug in 0.1, and how much you're off by depends upon how far you are away from the center, right? Okay, so that's why you're getting this dependence of the remainder upon the value of x, upon what you're actually plugging in. So just to get an idea of this process of plugging in a value of x when you're centered at 0, let's look at this approximation for sine. This is something you saw when you approximated sine in example 2 that you read through. Here we're approximating it with a cubic, and this is what the cubic looks like when you approximate sine at 0. Notice that the cubic matches f in terms of value, slope, as well as concavity, as well as the rate of change of the concavity, right, up to the third derivative here. It matches it at x equals 0. Okay, if you use this PE3, this third degree polynomial, to approximate sine anywhere else, you're going to produce a little bit of error, right? So for example, if I was to use the polynomial to approximate sine here, like at this value, right, at this value of x, okay, the polynomial would say that the value of sine there is what? 0, yes, okay, but we know that the true value of sine is actually up here, yes, it's right here, okay? So the polynomial is telling us that sine should be 0 at that place, and we're like, nah, not quite. The remainder that we're actually generating, the error that we're generating, is this distance right here, how far away they are from each other, right? This is the absolute error. We use the word absolute if we are only talking about positive, right? We don't care if it's an underestimate or an overestimate here, right? That's the absolute error. That's also going to be the remainder, okay? And notice that actually the size of the remainder depends upon how far away you are from your center point here, right? So your remainder here is fairly small, your remainder here is fairly large, your remainder over here is even bigger, yes? Okay, so the remainder depends upon x, right? It depends upon the x that you're plugging in here, where you want to use your polynomial to approximate the function at. Okay, let's get an idea of this by looking at one of our interactive figures. So let's look at figure where is it? Figure 10. Here we go. 9, 10. So let's use Taylor polynomials to approximate e to the x. This is kind of like example 3. Let's look at a first order. So that's with a line, right? This is what the first order Taylor polynomial will look like, the linear approximation. This graph over here is showing you what the remainder is for various values of x that you try to use your polynomial to approximate the function at. Okay, if you didn't catch all that, back up and hear me say it again, right? The idea is for various values of x, let's use this little slider right here. We're going to approximate it, or we're going to plug in a value of x, like for example 1, right? If we use our polynomial to approximate the value of the function at 1, our polynomial says, the value's here at 2, but actually it looks like it's more like 2.5-ish or something, right? It's a little more than 2.5. Notice that here the remainder at when you use x equals 1 is what? A little more than half, right? That's that distance right there. Yes? And notice that the remainder grows, the value of the remainder grows, the further x gets away from the center. Yes? When you move over here to 2, the remainder is fairly large, right? The remainder has grown very large, right? The remainder function here tells you the value of the remainder based upon the value of x that you're plugging in. It's really just telling you the difference between the function and the polynomial, right? So that's the first order. Let's look at the second order. Okay, so this is a, first of all, better approximation because now we're matching in terms of concavity as well, right? And notice that the remainder, of course, still increases here as x gets further away from the center. but it's not growing as much, right? If we compare the first order and second order, the remainder grows much more quickly for the first order than it does for the second order because, of course, the second order is a better approximation, right? Now let's include the third order. So let's take these away for a second and look at the third order. Much better approximation, yes. Even further away from the center, yes. These other two were not as good of approximations as the third order is, and you're noticing over here with the remainder functions that the third order one, the remainder is already much smaller than the first and the second order are, right, as x gets further away from the center. Okay? And of course, you can imagine this, that as you get much higher order polynomials, that the remainder is going to be fairly small, right? Okay, so let's continue on and talk more about the remainder here. So because of, we can't prove this in general because it would take us a little bit of time to do this, and you don't quite, I think, know the mean value theorem explicitly well. But because of a mean value theorem argument, we are actually able to get a specific way to express the remainder, right? So this is called Taylor's theorem. If f has continuous derivatives up to the n plus 1th derivative on an interval containing I, meaning in just an interval around I, right around where you've centered your approximation here. So for every x that's in that interval, for all x's in that interval around where you're centering it, right? So what this means is use any little x in around a, right? In a certain interval around a. Then we know that the function is equal to the nth order Taylor polynomial plus some remainder stuff, yes? Okay, because the remainder is the difference between the function and the nth order Taylor polynomial, right? Because we've just reordered the subtraction here, right? Remainder is difference between function and nth order, so function is nth order plus remainder. Good? Nth is Pn is the nth order Taylor polynomial for f centered in A. The remainder is the following. Again, this comes from a mean value theorem argument. If you want to get a little idea of how they're coming up with this, you can see the discussion on page 597. But the idea is that the remainder here for what's left over between for using your polynomial to approximate the function when it's centered at A, but plugging in x, right, the remainder is going to be given by the following. The n plus 1th derivative at C, okay, what is C? C is some point between x and A. The reason that happens is because of the mean value theorem argument, okay? C is just some number between the center and what you're using your function to plug in a value of x for, right? You're going to approximate at 0.1 or something, but it's centered at A, which is 0, for example, okay? C is just some number between x and A. All right, so the remainder is going to be the n plus 1th derivative at some c, we don't know what the c is, over n plus 1 factorial times x minus a to the n plus 1. Okay, again, this comes from the mean value theorem. Read the discussion on page 597 if you like for a little more background for this. The major problem with this is that we don't know explicitly what the c is. It just says for some point c between x and a. We don't know what that is, right? So how do we figure out what the remainder is if we don't know what c is? Well, here's the kicker. Usually, it is possible for us to figure out that this derivative up here is bounded, right? So, for example, if we're approximating sine or cosine, then the derivatives are always oscillating back and forth between sine and cosine, which means that they're always between 1 and -1, right? So we can bound the derivative usually up here. So that's where we get into this idea of estimating the remainder, putting a bound on that n plus 1th derivative, okay? The problem is, again, like I said, we don't know what c is, so we can't actually get an explicit form for the remainder, but we can bound it. So let n be a positive fixed integer, just so that we're talking about integer derivatives. Suppose there exists a number m such that you can bound the n plus 1th derivative by it. Yes, okay? What this really means is that this n plus 1th derivative is between m and, or negative m and m, right? That's all that means. Okay, the remainder in the nth order Taylor polynomial for f centered at A satisfies the following. I know this looks really complicated, but let's go back a slide and see if we can actually come up with this ourselves. Remember that we have this bounding, right? It just means that the derivative, the n plus 1th derivative, is well behaved, right? It's not doing anything crazy, right? It's going to be less than 1 or -1 or something like that, or -5, right? We're going to be able to bound it. So let's go back a second and use our little pen. Okay, if I wanted to look at the absolute value of Rn, right? Okay, the absolute value of the remainder, just how much we're off by. The absolute error is really what we're looking at, right? This is absolute error, right? Okay, so if I wanted to take the absolute value of this part right here, yes, that would mean taking the absolute value of this whole part right here, right? Parts of this can come out, right? Because we know that the factorial is always going to be positive. And so really we're just looking at saying, okay, put this absolute value of the n plus 1th derivative in here, right, at c. If I break this into parts like this, times the absolute value of x minus a to the n plus 1th, right? That's what happens if I just break the absolute value across all the multiplication that's happening here. There's one right there, and we break it across the division as well. Okay, once I have that written, using the inequality I have on the next slide right here, yes, because I know that the n plus 1th derivative is bounded by m, then that means this part right here is less than or equal to what? M over n plus 1 factorial. And then we get this absolute value, x minus a to the n plus 1. Okay, and that's exactly what we have on the next slide right here, right? We have the n plus 1th derivative bounded by m. All the rest of the stuff follows with absolute value around the x minus a. Okay? We'll do more of this together in class when we meet on Tuesday, but for right now, please read example number 5 on page 597 to 598. That'll give you an example of using this formula with estimating the remainder for cosine. And then again, we'll continue this together on Tuesday.